Welcome to Energy Talks, a regular podcast series featuring expert discussions on power system testing, data management, cybersecurity, and important trends in the power industry. My name is Scott Williams from the podcast team at OMICRON, and I will be your host. Hello, everyone. In our last episode of this two-part series about partial discharge monitoring, we talked about the strategic reasons for implementing a continuous monitoring system to assess the health of electrical assets. In the second episode, we're diving into the technical side of PD monitoring, specifically how it separates real PD signals from electrical noise and how to make sure the data you're getting is useful for your operation. It's all about moving from raw data to a system your team can trust. Joining me again are Daniel Gebhardt and Hendrik Schleifer, who are PD monitoring experts at OMICRON. They will explain how moving to continuous PD monitoring is ultimately about having better visibility into your assets so you can make more confident decisions. They will also walk us through SCADA integration and how to handle an alert when it happens. So without further delay, Daniel and Hendrik, welcome back to part 2 of our discussion about online partial discharge monitoring.
Hi, Scott. Thanks for having us.
Hi, Scott.
Hendrik, could you walk us through the setup of a monitoring system and how it works once it is connected to the PD sensors, to power, and to a network?
So in the typical setup of a monitoring device, you will have a so-called acquisition unit that you will install on your sensors or very close to the sensors. It's actually important that the cables coming from the acquisition unit going to the sensors are kept as short as possible, because otherwise they will start acting as an antenna and you will capture signals that are not related to your machine's partial discharge conditions. So that is step one. You could imagine this is just a box that you install close to your asset. And then depending on the system, if you, for example, have a temporary monitoring device, that would be it. So it's the box that you install and it monitors. But if you want to do fleet monitoring, you have a multitude of assets that you want to monitor. You would typically have multiple acquisition units, one for each of the assets that you want to monitor. And then there is a bit of infrastructure involved, because obviously you want to look at the data at one point, or you want to get a notification if something problematic is happening. So this would then involve a network connection to each of the acquisition units. And then this data is gathered typically in some server installation where you would then gather the data from all of your various acquisition units. And then you would have a software part that is processing all of the data. So that is essentially keeping track of continuously evaluating the data streams from each of the device, preparing the data for meaningful visualization for the end user. Because as you can imagine, there is just millions of pulses that we're recording in short intervals of time. It's impossible to look at this. So we have the machine prepare the data in meaningful views. So we have these tools. For example, the PRPD is a very powerful visualization tool, the phase resolved partial discharge diagram, that allows an expert to assess what kind of PD defect we're currently looking at. Other tools, such as 3-part, for example, allow you to, in a 3-phase asset, to actually distinguish various PD sources. So we call this clustering. You get a cluster for each individual PD source, which allows you then in turn to create a PRPD for this particular cluster and then just look at the defect. And a monitoring system's job is, I would say, the most important part is reliability. So it needs to run 24/7 and it needs to run all of the time. It's not allowed to, because of some hardware hiccups, to stop its work altogether. So a lot of mechanisms need to be in place for this to run reliably over a long period of time. Then you have a data storage aspect, because as I said before, it's millions of pulses that need to be reasonably managed. We need some logic that is processing the data and can keep it for a long period of time, so 5 to 10 to 20 years, and that you will still be able to look at historical data of your asset. And then again, you need the alerting aspect. So monitoring system that is just silently in the corner doesn't help anybody. You need a notification mechanism when something critical happens. So let's assume a PD source that was looked at over a certain point of time increased in charge significantly. that would be the point when you would raise an alert and that you have to communicate to the user. So that would be either via by email or, for example, in a SCADA setup.
How much operator involvement is required after a PD monitoring system is connected and running? You mentioned this is happening automatically. Can somebody who installs a monitoring system just leave it until that person is notified?
We have to distinguish. There is a certain commissioning part at the beginning. And maybe I'll try an analogy again. Measuring partial discharge in an online environment where the asset that you're monitoring is unfortunately never in a vacuum. There is lots of other things around, lots of other signals that we will pick up at the same time as the partial discharge.
And this is referred to as noise, external noise, right?
Exactly. Noise, disturbances, or even PD sources from a neighboring asset. So assume you have a rotating machine, you monitor it, and then on the same, there is a transformer connected next to it, and the transformer is having partial discharge effects. You might see them as well on your end on the rotating machine. For the analogy part, so the problem is very similar to if you imagine you're in a room full of people and everybody's talking at the same time. And you're really interested in just one conversation, but there's all of this noise around which makes it very impossible to pick up the individual conversation. You would need to set up a filter that just reduces the information to this particular one that you're interested in and tries to get rid of all of the surrounding noise. So this is, to your question, the operator involvement at the beginning or during the commissioning step, that you will have to configure the asset in a meaningful way so that it can actually look at the partial discharge. There is a certain risk if you do not configure this correctly that is similar to a surveillance camera. You point it against the wall, then you won't see anything. So that is the operator involvement at the beginning. But then as the monitoring system is running, essentially the operator involvement should be at a minimum. I would say it depends a bit on your level of interest. Of course, a monitoring system gives you a lot of viable information where you can continuously look at the development of partial discharge over time. I think this can serve academic purposes where you want to look into the development of partial discharge under various load conditions, for example. But in a typical use case, so if we, let's say, go back to somebody who's just interested in if there is a problem or not, then the idea for the PD monitoring system is that you do not have to interact with it. You just wait until you get notified by the system that there is something problematic.
There's an element of trust there. You're essentially trusting the monitoring system to pick up on a real defect, a developing defect, a potential problem. Tell me a little bit more detail. How do PD monitoring systems determine when there is a developing problem, and how are operators notified of the situation?
It depends on the levels of detail that we will go into. But maybe from a bird's eye view, it boils down to source separation, essentially. Like all of the sources that come in, you will need to filter them by origin. What helps us here is that a partial discharge defect has a fixed physical location, right? It's a point of your insulation that is getting worse, that's deteriorating. This is where the partial discharges actually occur. It's a fixed physical point. The assumption is now, as the signals that are generated by these partial discharge propagates to our acquisition units, they will always take the same path. The frequency response of these pulses as they reach our acquisition units have a signature that is very unique for this particular point. And using these information or this assumption about the partial discharge helps you build certain tools to sort the PD sources as they come in, using, for example, the three-part technique, where you have synchronous measurements over 3 different channels, and then you can sort the pulses as the aforementioned clusters, where you can then just look at the individual defects. You will also pick up noise this way, but if you have a mechanism in place that also does some pattern recognition on these particular sources and can say, this is noise, then the monitoring system will stop alerting you on this. So it will just disregard this, keeping track of it nonetheless, but not alert you. On the other hand, you will look at a certain cluster that has been identified. And if it is partial discharge, then you just look over time, and then the trend will help you immensely. You would just look at the charge of this particular source over time. And if it increases by a lot versus, let's say, the known acceptable level before, then an alert would be issued.
Okay, so given that, could you tell us why you don't necessarily need to be a partial discharge expert to make sense of what the PD monitoring system is indicating?
I think this depends a lot on how deep you want to look into it. In general, if the system is set up and commissioned, as Hendrik just explained to us, we are quite sure that you get an alarm once something of importance will happen. Means, of course, as soon as you get an alarm, in this case, you might need somebody with additional PD knowledge, not an in-depth expert, but with some basic PD knowledge to look at that alarm and to derive next action steps from it. Is there some immediate action necessary? Do I need to get some more information from the operation condition of the asset, some things which are not within the system, which exists outside of the system? And all these together form the picture so that you should, in an ideal case, not need the detailed information, because you can be sure that when the system alarms you, this is something meaningful that is happening on your asset. We should take action in terms of why it develops, why something changes, and if this is of direct importance to your asset. So basically, a good and solid commissioning is what takes this PD expert knowledge and puts it into the monitoring system in order to just give alarms when it's really necessary.
How do continuous online PD monitoring systems catch developing defects during peak loads when offline tests might miss them?
Well, I wouldn't directly say offline tests miss them. I think that's getting back a little bit to what we discussed at the beginning. The electrical stress on the installation is just very different during an offline test compared to the online situation. So it's not that we miss them. They might actually not be happening during our offline test situation. You can think about your three phases, because we have a three-phase system, and all the electrical stress of these three phases is, of course, overlaid in the asset. While if we do an offline test, normally we just have a single phase source, so the other two phases are either on a defined potential or grounded, and with this, there is not much overlay. So we are stressing our installation in a different way, and so we are not overseeing the defects, but we actually don't trigger them at all. We might be triggering other defects. That's okay. So if you have a good testing person, they can actually design an offline test to really stress specific points in the installation to have like a detailed look on that. But nevertheless, planned overstressing of one part leads to reduced stress on the rest. So you are never in the real online situation. And that's the big advantage of monitoring. We are actually looking at the electrical stress the installation sees all the time.
One other aspect that is important to a lot of asset operators is that such monitoring systems are compatible with their other systems. So we are hearing a lot about industrial Internet of Things. How do OMICRON's monitoring systems integrate with modern SCADA systems, for example, to make data more accessible to decision makers?
We support a variety of well-established protocols to propagate our data to a different system. So, you could, for example, say you can use the IEC 61850 protocol to get data from our systems. Or you could be more old school and use the well-established Modbus TCP protocol. So there is a certain range of configurable options that you can use. So basically what best suits your needs, we would then be able to provide these protocols. Like oftentimes you can also use a converter or something if it's some protocol that is not supported. But in the end, then you get a free range of configuration options. So essentially there's a couple of scalar values that the monitoring system records periodically and measures every second. That would include most prominently the charge value, obviously, as well as the PD rate, if this is of interest to you. And with the OMICRON monitoring system, it's freely configurable what you want to get for your SCADA integration part.
Once an operator has been alerted, what essentially are they looking at to tell them that maybe there's a problem and they need to take action? Can you describe how this process works?
Well, as you said, the operator is alerted. They look at the system, they find some data, they find details, they find PRPDs about the defect, they see how it was developing, and this gives them a first indication. Obviously, if I have a defect which is like very slowly sneaking in and just hit my threshold level now, but I see in the trend that it's been developing over the last 3 or 6 months, then I don't need to stop the machine. If, on the other hand, I do have a defect which just hit and where I see a development within the last 2 or 3 days, like a steep development, then that would be one thing why the operator should think about next actions. Additional expert information, be it by the system itself, as it might give you a pattern recognition term telling you that this pattern is a surface discharge, that this pattern is a slot discharge, or by additional experts which evaluate that pattern in this specific case. You can then derive next actions. The very good thing is that, especially if we talk about machines, they don't die from today to tomorrow by PD. As we said, it's a smoke indicator, so I should be able to take my actions early enough and do well-based decisions and not run in fear that my machine will stop working within the next hours.
So we're going back to that indication that offline testing itself is not unreliable in the sense that it does not uncover things that a monitoring system would find. It's simply that you have something continuously looking at the situation to cover that time in between diagnostic tests. Is that correct?
Yeah, that's more or less correct. I mean, one example which happened more than once is you are at a machine or at an asset and you do a PD measurement there because it has been triggered by whatever reason, either by some external influence or because they did some changes on the machine whatsoever. And then you realize you measure some PD in an online situation. And then the big question comes up, and that's also for older machine. It's like, was that there before? Because we didn't have any online PD measurements, or at sometimes we didn't even have PD measurements of the very same asset for a long time before. So without having that history, it is hard to assess if a certain PD, no matter of what level, is critical to an asset, or if this might have been the situation this asset has been living in for the last 10 to 15 years without any changes. And we are again at the point of the developing trend. If I do see a trend development, that is something where I need to take care. And if I see a rapid trend development, that's something I need to take action. It's not the absolute level which is counting. So that's why single spot measurements are never really giving us a good impression of what the status of the installation is.
In both of your opinions, why is continuous PD monitoring becoming a must-have rather than a nice-to-have, especially for that peace of mind?
From this modern day and age, we live in a data-driven world. It is just very helpful to know what is going on with your machine. And I think PD monitoring is an essential building block of creating a good understanding of your asset's health. And I think Daniel mentioned this before, it's by far not the only indicator of your health of your asset, but together with other parameters, temperature, vibration in rotating machines, whatever you have, the more of those data points you gather at one point, the closer you get to build a clear picture of the asset health of your machine. And continuous data, and that is what an online monitoring system will provide you with, it just gives you a very clear picture of what was going on, a complete history of the development. Whereas if you do spot checks, they're very good and they're very helpful. But if you really want to go into the direction of building this larger asset health view, you need the continuous data to look at the developments over time. And I think this is, and Daniel also said this before, the key aspect. You just get this gap-free picture of a long period of time where even if things are present, as long as they do not get worse, you get a good sense of if this is acceptable or not. And I think this is where the PD online monitoring really helps you.
Yeah. Another aspect, of course, is we do have fewer people who need to take care of more and more assets. So the workload in general increases. They need to be much more versatile about the tasks they are doing on or around these assets. This means if I do have a monitoring system which gives me a little bit at least peace of mind about one aspect, and that's in this case the installation condition, I have something I can take off my mind and I can just trust and rely on being alerted if there is something important to change.
If you could give one piece of advice to an asset manager or even to a maintenance engineer, what would it be?
Give the PD monitoring a try. It, I think, generally is very helpful if you're interested in the topic to get an overview of what is happening on your machine at all times and the various developing defects.
I would also say if somebody is already, and that's the first and good start, doing like spot measurements, even maybe during maintenance, and gets a first idea of how the installation condition of their machine behaves, I would definitely say advance that picture, go to online measurements and really get that question off your mind and have a monitoring system which is collecting this data and really raising its hand as soon as something changes. It gives you the chance to do a more reliable planning, to have an idea, is there something coming up or not? Even if you don't do the very detailed planning, but you have an idea about the condition and you might know if there is some extensive, or if you might need to do more detailed look on the winding heads, if you might want to add an additional spare day for whatever tasks you are planning, or if you might even say, okay, I can cut it short. I'm sure that my PDs and my installation conditions are good, so I can maybe shrink some of my maintenance tasks. Like even if you don't get away from your scheduled yearly maintenance, you do gain some flexibility on how you do this maintenance, how you plan it. And also here, you have the peace of mind that if something unexpected is coming up, maybe on a different asset, that you can say, okay, for that machine, I'm sure I do have a monitoring system on it, and I'm honestly very sure I can skip that for the next half a year and push it back and take care about whatever unexpected happened on another point.
Now, why should asset managers and maintenance engineers feel confident when using OMICRON PD monitoring systems to continuously assess the condition of their electrical assets?
I would say because we know PD. We have a very long history about PD measurement with very high precision on different fields as a company, and also moving into the monitoring market already quite some time ago. So I would say partial discharge is something which is actually within our blood. It's not that we stepped on a developing trend at that point, but we actually can measure a developing trend.
Yeah, I also want to add that we have experience with monitoring for way over 15 years now, and generally offer a very reliable monitoring system. So something that just continues running 24/7, has well-advanced noise suppression techniques, gives you the option to look at the individual sources. And overall also something maybe in the background, as Daniel mentioned, we have a lot of PD experts and we have a support that is readily available 24/7. We offer a high quality and a high level of detail of PD information even after the alert has occurred to look into the data that gives you just the overall picture in terms of PD, what is happening on your asset.
Regarding the reliability, maybe one aspect, we are just in the process to decommission a PD monitoring system on a rotating machine. And that's not because the system failed, but it's because the machine is now going out of service after almost 17 years of monitoring continuously 24/7. So that's just one very recent example of the reliability of our monitoring systems.
Daniel and Hendrik, thank you both for joining me and sharing your knowledge about online PD monitoring in this two-part series of Energy Talks.
Thank you very much, Scott. It has been a great pleasure, and hope to be here another time in the future.
Definitely.
Thanks for having us, Scott.
Well, thank you both. And a big thank you to our audience for listening to this and other episodes of Energy Talks. We always welcome your questions and feedback. Please send us an email to podcast@omicronenergy.com. OMICRON has several years of experience in power system testing, data management, and cybersecurity, and offers a matching solution for your application. For more information, visit our website at omicronenergy.com. Please join us for the next episode of Energy Talks. Goodbye for now, everyone.